All right. So, everybody, we're going to be going over communication interfaces. This is basically a bunch of different protocols that we use on the car for electrical communication. And it's not just the car, like these are used across industry standards. So, um, which button do I have? All right. So, why are we learning about this? Companies love to ask interview questions about different communication protocols. So that's a big one. But also, we just like they love to ask questions about it because it's important stuff to know. Um, because if you want two boards, chips, systems, whatever, to talk to each other, you're gonna need communication, right? Also, on a team, we all need communication between each other. That's how we get things done. Communication is very important. Um, and honestly, systems that can't talk to each other are kind of lame because like then you can't get any information and you can't do any cool computation or decision making because you have no information input or output. So these are really important, and every bus that we're about to talk about is somewhere on the car. So you're gonna run into this at some point. And if you know how it works, your life will probably be a lot less painful than if you don't know how it works. Um,
When you say every bus, are you talking about every communication?
yeah, every communication protocol that I'm about to go over is somewhere on the car. And as we go through them, I'll tell you like an example of where each one is used, but there's more than what I'm giving here. So the first communication protocol, and some of you might have heard of these before, but it's good to go over them, is UART. This stands for Universal Asynchronous Receiver and Transmitter. So it's just two wires. Your chip will have a transmit and a receive pin, and then the other chip will have a receive and transmit. So, right, one transmit connects to the other one's receive, and the other one transmits to your receive. And so you pull, both of the lines are usually high, and you pull your transmit low in order to start transmitting. So it's basically like they're both sitting high. I pull my transmit low, so the other one knows I'm starting to transmit. And the length of your messages and the speed, which is also called baud rate, need to be agreed upon before starting the bus. So you guys will typically set this up in the STM32 Cube IDE. You'll set like your baud rates and your clock speeds. And then when you scope it out with an oscilloscope, you'll be able to see a waveform like this one on the bottom, where you can see the start bit, and then you'll be able to tell high or low, and you can actually decode messages on an oscilloscope. Typical baud rates are like 9600 baud, or a lot of times we'll have 115,200 is a common baud rate. And information on the line gets read into a buffer and then gets sent to the memory of the chip. So that's more on the CS side, like your memory management. You're getting in a byte at a time, and then you send it into memory. Typically, it'll just be two devices. This is like it's just a transmit and a receive. So it'll just be two things talking to each other, and you directly connect transmit to receive. And an example of where this is used is on microbasic, talking to your computer over what's called serial, or like the serial monitor. So when you plug your computer into the ST link, and then the ST link is plugged into the microbasic, the ST link and microbasic have a debug UART bus that they're using to talk to each other. So when you guys see stuff popping up on your computer, that's UART. So if that's not working, you could actually probe this bus and see if this is the issue or something like that. Um, and like I said, this presentation will be quick. There's much more that you should know about this, but I know that just standing up here and like talking to you about it won't like actually help you remember it. So I have resources at the end, such as like Analog Devices and Texas Instruments have really good application notes on each of these communication buses, um, that you can read. But yeah, is anything unclear about like simple overview of UART? Yeah, Alex.
So it starts high. You do that with like a system that goes high, and
Yeah, so UART doesn't use pull-up resistors, it uses push-pull, which we'll go over at the end of this presentation. But yeah, it's not a resistor, it's a switch. Yeah, it's basically when I say pole, it means there's something on the bus connecting this communication line to your supply voltage. Because you can think of every piece of copper on your circuit board as a capacitor, and you need to charge that capacitance to the voltage that you want it to be at. Yeah.
Situations where you can change the baud rate, you're just keep it at 9600 watts per second.
Yeah, so the baud rate is something that you usually have to set up in the parameters of the bus. So you're typically not going to change that on the fly, like during communication. But if your baud rate wasn't able to, like you didn't have enough bandwidth and you weren't able to send enough data, you might want to have like change the settings of both devices to operate at a higher baud rate. Um, Once you get past 115, there's some more things you have to think about for higher speed communication, where there's like some extra serial pins that you'll need to make sure you meet timing. Yeah. Yeah.
Can like each transmit and receive one have like different operators?
So like one microcontroller could have two UARTs connected to different peripherals, and those two UARTs could be operating on different baud rates. But it's not like it wouldn't be like I'm transmitting on one baud rate and I'm receiving on a different baud rate. It wouldn't do that. Yeah, sure.
What does the asynchronous mean?
Yeah, so asynchronous, that's a good question. Asynchronous means that there's no clock signal. So you're simply just sending your communication. So there's no clock. So it's not like I'm looking at a clock and I read the data every rising edge. You don't have that. And the way that UART does that is because they agree on the baud rate beforehand, they'll see that you're pulling this low. They will, after it gets pulled low, they wait half a clock cycle and then they start reading every baud rate. So it gets pulled low, I wait until the middle, and then I just read. So you're reading in the middle each time. And so even if you have some like jitter or skew and you sort of drift one way or the other, you start in the middle and it counts on the messages being short enough that even if I read like here, and then I read like halfway, and then I read like towards the end, the messages aren't long enough that you could like shift out and get an incorrect bit.
Sorry.
Yeah.
How long does that have to wait to like signal that it's starting like the frame? Like
Just one bit width. So the line will be high and this is not being used. And then I want to transmit, so I pull it low for one bit. So like one baud. And then I can start transmitting. Yeah. So like for a 9600 baud rate, that's 104 microseconds per bit. So I would pull it low for 104 microseconds and then 104 microseconds per bit. Yeah.
What's the buffer?
So on the receive side will be our other chip. And so this is sending serial, right? Like if I was just at the other end and I was just looking at the line, I would basically see like 1, 1, 0, 0, 0, 1, 1, 0. So I'm only seeing one at a time. So I basically imagine I had like 8 boxes behind me and I see the first bit and I take it and I put that in the first box. And then I see the second one and I put that in the second box. And then I see the third one, I put in the third box until you get 8. And then you take all 8 boxes and you put that into memory. So that's how basically I'm turning it from a serial, like I just see one at a time, to parallel, like 8 in a row.
So it's basically just collecting and then.
Yeah. Yeah. And those boxes that I'm talking about are basically registers. A register is like a way to hold memory. So like each bit in memory is stored in a register. And I can talk about like different types of registers and how they work. But like if you look up like a D flip-flop, that's like a really common type of memory. And it's basically just a input, output, and a clock. And it just takes its input and stores that value every clock cycle. So a register is just like a place to hold memory that stores zeros or ones. Yeah. Mhm.
Like at what point does this like, when it goes like high again, like at what point does it say like, okay, we're not like doing any more messaging anymore?
Oh yeah, so they agree on the data length before you start transmitting. So that's like something you would set up in the settings of the code for each one. And so as soon as I count the number of bits I want, I actually stop looking at it. Yeah, so if the transmitter and receiver didn't agree, the receiver would only read the first however many bits it agreed upon. Yeah.
I know when you create different communication circuits, what applications like UART like typically used over like CAN or like some of the other ones?
Yeah, I'll have a comparison in after we go over the next two, but that's a really good engineering perspective to take. That's a good question. Yeah. And also like great questions, guys. I'm so glad that like you guys are engaging with it. All right. Okay. All right, so the next one we're going to go over is I2C. Um, some people say I2C, some people say I squared C. Technically the standard calls it IIC. I don't know. IIC sounds kind of silly, but it stands for inter-integrated circuit. So this communication is meant for on board. You wouldn't be using this communication like between PCBs with a harness or anything. It's meant between two integrated circuits on one PCB. So this has two communication lines. You have SDA and SCL, which stands for like serial data and serial clock. And so this one is synchronous, right? We have a clock signal that we're going to be reading the data on every rising edge. And so this communication has one controller and many peripherals. Some of you might be aware of the terminology of like master and slave in chip communication, but we're trying to move to more neutral terms. So now it's controller and peripheral. And I2C can actually have multiple controllers, but things get a bit more complicated. So this, I'm just telling you about the simplest case. If you guys want to create a bus with multiple controllers, you can read the I2C spec. Honestly, the I2C spec isn't very long. Like if you read the TI application note, it's like maybe 30 pages or something, and like 5 pages of those are reference. It's like less than an hour to read it. So like I said, intra PCB communication within one PCB. And the message structure is you're going to send the address and then the message. So we're just talking one to one, right? Like I always know who I'm talking to, and I always know who is talking to me. There's only one way to talk. But multiple devices might be connected, like this diagram on the bottom right. So I have to send my address, and then I have to send my data. And also, the controller can talk to the peripherals, and the peripherals can respond to the controller. So it goes both ways, which is what we call, well, actually, it's not, I need to update, this is wrong. It's not simplex, it's called half duplex. So duplex communication is like you can both talk to each other at the same time. Half means I can talk to you or you can talk to me, but not at the same time. Simplex is like I can only talk to you or you can only talk to me. Yeah.
Or in the CAN is bidirectional.
Yeah, so the CAN bus would also be half duplex because I can talk to you and you can talk to me, but not at the same time.
What's bidirectional?
Bidirectional refers to like I can talk to you and you can talk to me. If you were able to do it at the same time, that would be called a duplex communication. If you can't do it at the same time, that would be half duplex communication. Simplex is like I can only tell you or you can only tell me. So yeah, sorry, that's an error on the slide. I2C is half duplex. And then this is an open drain clock. We'll talk about that later, so we'll skip over that for a second. But this is used for if you're familiar with the TPS 2482 chip, if you looked at any of our circuit boards yet, this is on every PCB on the car, and it monitors the voltage and current on every PCB to do all of our power telemetry. And it uses I2C to talk to the microcontroller. And honestly, I think its libraries need to get updated. So if somebody wants to like make sure all the I2C drivers work correctly, so that we have better power telemetry, that would be very useful.
The data.
Yeah, so when I want to start communication on I2C, I will pull down the data line to say I want to start, and then I'll pull down the clock right after that. And then the clock will basically just toggle up and down at the, like this is also another one, you have to determine the frequency or the baud rate beforehand. And my clock will just go up and down, and every rising edge, it'll read what the value of the data line is on that rising edge. So it'll be like 0, 0, 1, 1, 1, 0. And so it'll clock in a new value every rising edge. Exactly. So like in between clock cycles, I could literally go like up and down and it wouldn't see any of that. And then it would just see what's on the next rising edge.
So just turn the clock speed super high to make sure it's like make sure it's.
Yeah, so that's an excellent question. So if we turn the clock speed higher, remember what I said earlier about how like every piece of copper is like a capacitor on the board. So making this go high and low, you're actually charging that capacitor from VDD and then dumping that power into ground. So because you keep charging it and then basically discharging it, you're actually using power. So if we increase our frequency, we have to charge and discharge more per second. So it's going to cost more power. But we could talk faster. There is an issue with the open drain that we'll run into. But like I said, we'll talk about that in 2 slides. But yeah, it's basically a trade-off between do I want to spend more power and talk faster, or am I okay with this data rate and I want to save power?
How much extra?
That's a very good question. That's actually a 151 midterm question. So the energy that's stored in a capacitor is equal to 1/2 capacitance times voltage squared. So you're putting that much energy into it and then getting rid of that much energy every time you charge. So if you multiply that by like your period, like how many times you're doing that per, like how many you multiply by your frequency, which is how many times you're doing that per second, then that would give you the total amount of like power that you're dissipating. So if we were to double the speed, it's 1/2 CV squared times frequency. So it'd be twice as much. But if you were to have your voltage, right, if we could have a lower logic level, voltage is squared. So if you have the voltage of your logic level, you could actually quarter the amount of power you're consuming. Or also if you halved your capacitance, you could have the amount of power that you're consuming.
Just use a small capacitance. Don't that as much power.
Because like a capacitance charges with like Q equals CV, right? So the current is equal to the capacitance times the change in voltage. So if we had small current noise and a smaller capacitor, it would change your voltage a lot more. So if you had no capacitance, this bus would change really easily, which means it takes less work to change it. But that also means noise has more like power over it because the strength of your noise isn't changing. So if I make it easier to move this node around, then noise will move it around more. Yeah.
What's typically causing the noise just in general with these communication networks?
Yeah, I mean, there's a bunch of stuff like there's external sources, like the grid is 60 hertz. So like sometimes you'll just be looking at your oscilloscope and like I had a really bad laptop power supply once and I was probing a board next to it and you'll just see 60 hertz get picked up on your oscilloscope probe because the power supply is switching at 60 hertz to take grid power and put into your laptop. There's also just electrical noise in the air, right? Like photons are hitting everything from the sun and like energizing things, and electrons are just whizzing all over the place. That'll just cause a noise floor on your communication. So you need to stay above that noise floor. Then on your bus, I mean, on your PCB, you might have like a higher speed communication that is coupling to this communication. Like if you remember, like circuit, or I don't know if you were there or not, but we talked about circuit fundamentals last week. Every piece of copper sort of makes a capacitor with every other piece of copper in your board. So if there's a capacitor between those two, and the impedance of the capacitor reduces with frequency, if I have a higher communication, it'll sort of just couple to that lower communication and it might add more frequencies on top of it. Yeah.
We have the clock ready beforehand, why do we need the clock?
Yeah, so this is so UART is much slower than this. So we can just read, and even if there's drift, we probably won't drift far enough to cause an error. But I2C, you can communicate much faster. So you need something that helps you time better to know when to read. Otherwise, you might get out of sync and you might be like reading a bit too late or reading on a transition. This also gets a little bit into like how digital memory is stored. You have a clock signal because, like I said before, we have a flip-flop, which is like a way to store memory. And you need a setup time. Like you need the data to be good for amount of time before you latch the memory. And then you need a hold time. So the data needs to be good for amount after the clock cycle. So to respect those times, that's what you have the clock. Yeah.
Here's all the clock and how it works, because like why can't we just keep the clock in? So is it like a timer or?
Yeah, it's basically like a timer. It's like telling you to like read.
Oh,
Read.
got you, so it's not like have it on the timer.
No, it's going up and down, and then it just reads every rising edge of the clock cycle. Yeah.
Only turns on when we have some like data we want to send, right? Otherwise it's on.
Right, exactly. Because you would just be charging and discharging that capacitor for no reason. So it only turns on when you have data that you're going to send, or like when a message starts. Yeah, that's part of the open drain clock. Which, yeah, I guess these slides are a little bit out of order. We'll talk about that in 2 slides, but yeah, I'll just save that. But yeah. Any other question? I love all the questions, by the way. This is awesome. All right, so the next one is SPI. SPI stands for Serial Peripheral Interface. And this is full duplex because we have the master out slave in communication line, and we have the master in slave out communication line. Also renamed to like copy and pico, because like controller and peripheral. So if you see that, it would be like controller out, peripheral in, copy, controller in, peripheral out, TPO. I don't know. I haven't seen any data sheets that use controller and peripheral for SPI yet. But what's different about SPI, number one, we have this two communication lines, so the peripheral and the controller can talk to each other at the same time. Then we have the clock line once again, so we can clock our message. But we also have the chip select, also sometimes called slave select, SS, or CS, chip select. And this is pulled low depending on which chip I want to talk to. So all the other communications we talked about, right? All those wires are shared. This one, clock is shared, MOSI is shared, MISO is shared, but chip select is actually a different wire per peripheral that you want to talk to. And you only pull the wire low for the peripheral you want to talk to. So you don't need to send an address because I'm pulling the line down for which one I want to talk to. Like I already know which one I want to talk to. So you save some data bits because you don't need to send addresses. You can just send more data. So SPI, as well for that reason, and it being a push-pull clock, can communicate much faster. This is also out of order, push-pull, we'll cover in a second. And this is used by thermocouples and many more devices on the card. Thermocouples is just the first one I came across when I was writing this slide. And there's an example of communication you can see over there. We pull chip select low, we start our clock, and then MOSI starts sending data to the peripheral. And you can actually, you don't need to let chip select go back up. You can wait and then send some more data. Or in this case, I think this, no, we're sending more data because MOSI is active. You could also pull chip select below, send a message to the peripheral, say, send me this data back, and then it'll start sending you that data back at the same time as you are maybe requesting the next piece of data. And that's why full duplex is good. Yeah.
And you have.
Yeah, so that's sort of a trade-off between I2C and SPI, right? Like I2C, we don't need to use hardware resources, right? Like we don't need to route more lines, but we're using more like bit resources because it's going to take longer to transmit. SPI, you can route as many chip selects as you want, right? But you might run out of GPIOs on your master controller. So there's more hardware resources. It'll take up more space on your PCB, but then you have like more data space. Yeah.
So each chip needs its own chip select line.
Yes.
So for this diagram, you have to have two of them, right?
Yeah, so these ones are like all shared and then these show it branching off. Best practice would actually be like draw a dot right there so you can tell that this is connected and that's not connected. So like this is one chip select, this is the next chip select, and then these are the shared data lines. Yeah.
Do that like in the STM cube ID or something like that?
Yeah, so you would set up your SPI bus and define the pins in the cube ID. Yeah. Yeah.
So is speed between SPI and I2C like similar?
No, SPI is usually much higher speed than I2C. Yeah.
Like this. The Mussell one and the Mussell, are they like corresponding ones and then ones leading into the other?
Yeah, so MOSI is gonna be when my master wants to send data out and I want the slave to input that data, that's MOSI. And then when I want data from the slave to go out and go into the master, that's what the arrows are showing, is which direction like data is going. So like the master will drive the clock and will drive MOSI, and then the slave device will drive MISO, and then the master will drive chip select.
So only the master has.
Right, the master is the one driving the clock, yeah.
Or is it just turn on whenever it needs to send or receive?
It once again, it only turns on when you need to send or receive. Like in the waveform on the bottom right, it'll turn off because once again, we don't want to waste all that power switching when we're not communicating. Yeah.
I'm so confused on how it works.
It's all good.
Not, it looks like it's not in sync, and it was like that for I2C too, like the block not in sync with the MOSI, so.
Yeah, so that's it's in sync with the edges, not with the high and the low.
That's up the.
Yeah, so like the edges of the clock, I mean like these vertical lines. So we only clock data on the rising edges. So you can see this rising edge lines up with like this being high, and then it goes low to wait for like the next rising edge. So we'll only clock data on the rising edge of the clock. So, and up until that rising edge of the clock, you need setup time. So the data needs to be like good and solid for some amount of time before the rising edge of the clock. And then you need hold time. So sometime after the rising edge of the clock, you need to keep it steady until the hold time is up. Yeah.
Why is the clock suddenly turned off for a bit? Is that just because there's nothing?
Yeah, I think it stops transmitting and then it starts transmitting again. But it's still talking to the same chip, so it keeps holding chip select. All right. Okay. So which one should I pick? Here's the table that I found. That just does a pretty good job. Right here where it says like RPI, that's Raspberry Pi. So they're just saying like, oh, if you used a Raspberry Pi. I mean, the first question is like, how many devices do you need? UART is one device to one device, right? SPI, you can have a lot of devices for hardware. I typically say if you need a lot of devices, I would lean towards SPI. But it depends, like, there's different use cases. Like, if they don't need to communicate as quickly, I would use I2C. And I think this one doesn't say the device limit, but one of the other reasons, which we'll get to when we talk about push-pull clocks versus open drain clocks, is the more devices you put on your I2C bus, it'll actually become harder to drive the clock and you won't be able to drive it as quickly. So SPI will be better if you had a big network and this clock line was going like everywhere. It would be easier to drive it with the way a SPI bus does, which is why I would lean towards SPI for more devices. But if they're all really close to each other, you could use I2C. Yeah. Oh yeah, sorry. I think the slide is after this one or maybe after CAN. After this slide, I'll jump to the open drain and then I'll come back to whatever I had after this. But I should really explain that first. But yeah, I'll come back into that a second. And then how fast do you need to be? So here's some example data rates. Like UART, if you're going pretty slow, you can do like 20 kilobits per second. I would actually say you can get higher than that with if you just increase your baud rate. Like that's pretty low baud rate. UART, you can also get into like if you add 2 more pins, you can do like this version of high speed UART where you get much higher baud rates, but the timing is a bit more tricky. But like I2C, you can get up to 1 megabit per second, and SPI buses can go up to like 25 megabits per second. For reference, the CAN bus, which we'll talk about in a second as well, we run it at 500 kilobits per second, but ours could go up to a megabit per second, and there's a different protocol for CAN that can go up to 5 megabits per second. What else? Oh, like I was saying before, faster clock is more power, right? Because we have to charge and discharge that capacitance. So like UART is medium power, mostly because it's just restricted to 2 devices. I2C is medium power, and SPI is lower power because your transmissions are shorter because you're using chip select. And the distances are different as well. Yeah, is there any questions about trade-offs? Yeah.
Would you like I2C or SPI? Because like looking at that SPI is faster and it uses lower power. So like
Yeah, I mean, let's like the speed is nice, right? But faster speed means more power. So let's say I want to draw less power. I don't need to talk as fast, and these devices can use simpler communication like I2C. Then I could save a lot of power if I just used I2C. Also, if the devices are close to each other, I2C can actually be more efficient than SPI in some cases. And I2C is also simpler. So if I want something that might be slightly more robust, might not break as much, like that's not to say SPI isn't reliable. SPI is also very reliable, but if it's simpler, then there's less things that could go wrong. Like if I don't need all the bells and whistles that SPI provides me, I2C might work better.
in that case, when it says lower power in the SPI column, is that for each individual clock connected to each device, but the line is shorter than chip select, or
Yeah, I think they're trying to say that SPI is lower power because as we'll see on the open drain versus push pull, I2C will charge up its capacitance through a resistor. So some power is getting burned by that resistor, and SPI will just short its line to power ground. So there's much lower resistance, so you won't be burning any power across that resistor. I think they might be trying to refer to that. Yes, that basically just means can the peripheral device say like, yes, I got your data and understood it or not? And then when it sends data back, can the receiving device say, yes, I got your data and understood it or not? Yeah, so like I2C and SPI have no acknowledge and UART does have an acknowledge. Yeah.
For SPI, why is it still considered duplex if it's all synchronous? Like, if you can't send messages between two things at the same time, wouldn't that be like half duplex?
Synchronous just means if you're using a clock or not. So if you're using a clock, you're synchronous. And you can send data back and forth at the same time. I think this video that I took these resources from for I2C is a little bit out. Their information's a little bit wrong because I2C isn't not like full duplex. But yeah, synchronous is if I use a clock or not. Duplex is if we can talk to each other at the same time or not. So it's the difference between like having a clock or having two communication lines. You can have both or neither.
If this is all powered by like a 24-volt LVDP,
Yeah.
like have you ever had a problem where it's like draining too much power from that?
No, we haven't really run into any power issues with low voltage communication. The entire low voltage PCBs only draw half an amp of power. Our main power concerns are like the coolant pump, the radiator fans, and the accumulator fans, because those can draw like in excess of 10 amps. Yeah, Alex.
It could also be that like, some ICs don't have I2C or SPI. Typically,
Yeah.
doesn't have those or.
Yeah, I mean that's a very real engineering issue. It's like sometimes the chips that I want to do this function, the designers just only give them a SPI bus or only give them an I2C bus. And usually that's for a reason. It's like, oh, if you want to do this thing, you should probably use this type of bus. So we're only going to design the chip with this type of bus. Yeah.
I'm noticing the comparison, is there generally a trade-off between the complexity of a communication set and the amount of distance it can travel? Like for.
Yeah, oh, a little bit. I think this might be too small of a sample size to make that type of assertion, but yeah, typically if things are more complicated, a lot of the complexity that they added is allowing you to communicate farther. Yeah, Allison.
Just to using a clock system.
Yeah, I mean, the advantages of using a clock is you can talk faster because you know that the clock is going to time you properly, so you could communicate faster. But you're also going to be using more power because the clock is basically just charging and discharging a capacitor. So if you had no clock, you might talk slower but less power. But yeah, the biggest thing is like just keeping everything in time. Also similar to a human issue where you need a project manager that's sort of like keeping each engineer in time so that like everybody's rowing in the same direction. Also, there's a rowing metaphor. You have the person in the back of the boat who's like, row, 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 right? It's like, well, why do they need to be there? It's like, oh, so we can row faster because you just row when they say to instead of each person independently thinking. Yeah.
Doesn't make basically have like all three of these or like.
Yeah, you can so when you do the STM32 Cube IDE, you assign the pins before you start working on your code. And so you would assign like these pins to be a SPI bus and these pins to be an I2C bus. And there's only certain pins that have functionalities for certain buses. So when you're an electrical engineer, you need to make sure you actually connected the correct I2C pins to your I2C device and you have the correct pull-ups. And then you work with the CS engineer and it's like, okay, these are the pins we need to set up. Here's the speed the bus is going to communicate at. Yeah. Awesome. Okay, I'm gonna skip ahead a bit so we can talk about clock types first because I feel like it'll make more sense. So there's two clock types, push-pull versus open drain. And these aren't just clock types, these are also just like ways that you can set the voltage on a net. So it's usually used for digital communication, but you could use them for other things as well. So push-pull is basically just two switches, and I either short the top switch to my output or short the bottom switch to my output. So these will have some small on resistance because these are MOSFETs, right? We have an NMOS and a PMOS. There'll be some small on resistance when we drive them high. And then it will basically, on this output pin, you can imagine there's a capacitor here. Because like this device is going to have some capacitance. Then you're going to have the trace going out across the board. And there's a ground plane below that trace, right? So there's some capacitance between that. And then when I get to my load device, it probably has some MOSFET on the input. And then I'm going to have like a gate source capacitance. If we can go into this more, but once you start looking into MOSFETs more, there's capacitors all over the place in this thing. I guess there's capacitor ground to source, or not ground, gate. There's a capacitor gate to source, there's capacitor gate to drain. This itself is a capacitor, that's why it's drawn like that. So there's a lot of capacitances to charge, which is why that's like basically what we're driving. And that's why you can get, oh, it's not on the slide. There's supposed to be a photo here of like a sharp clock and it goes up and down very quickly. And the reason that it's sharp is because this acts like a current source. And so it's a constant current charging a capacitor, right? So if we go back to first order principles, Q equals CV, take the derivative of both sides, dQ dt is current equals capacitance times dV dt. So if I have a constant current divided by my constant capacitance, it's going to be a constant value for the change in voltage. So it's a linear function. So it'll be like a slope. And then that's different than open drain, which is where the pull-up resistors come from. So when you saw the pull-up resistors on that other diagram, you basically have a switch inside of your driver that goes to ground. So this is an NMOS, and either it's closed or it's not. So when it's not, you basically have an RC charging, right? You have power over a resistor to the capacitor. And so you're burning some power there, right? Because the power dissipation of a resistor is V squared over R or I squared R, right? So there's going to be some energy turning into heat in there. But that's what gives you this waveform on the top right where it'll charge and then discharge. And that's what's limiting the speed of I2C because you have the RC charging for the rising edge and it's curved. So you need to wait for that to settle. And so the more you want to increase that edge, the lower your resistance is going to be. But the lower our resistance is going to be is, I'll show you how to calculate the discharge path. So you see when the transistor is shorted to ground, right? We're discharging the capacitor. You have to sink current out of the capacitor to discharge it. But the resistor is still connected to power. So we also have to pull current over that resistor to cause a voltage drop across it. So let's say we got eventually discharged. There's no energy in the capacitor. For VCC at the top to drop across RP to be 0 at the output pin, if we want a low, if RP is like 1 kilo ohm, then you're going to need to, and let's say VCC is 1 volt, then you're not going to need to drop 1 milliamp through that switch for a 1 volt drop across the resistor. And now if we half the resistance, we have to double the current, right? Going back to first order principles, V equals IR. So we have the voltage. If the resistance is cut in half so that we have a higher speed, the current needs to double so that we can hit a logic low. So that's sort of why I was saying it's simpler. It relies on the physics of RC charging, but that also makes it a bit slower and you're spending a bit more power. But you know it's going to work because like it's just physics. It will charge and then when you discharge it, it will discharge. But once again, that's not to say push-pull is like a non-reliable source. It's also pretty reliable. That was a lot. Please ask questions. Yeah.
Like how does the internal signal like drive actually drive the push?
Yeah, so a little bit into like MOSFET at device physics. So like this is the MOSFET here on the bottom left. And this is a NMOS, so it turns on or off based on the voltage between the gate and the source. So VGS, the voltage across here. And so for an NMOS, when VGS is greater than the threshold voltage, this will turn on and start conducting. There's a little bit that I'm skipping over where like there's intermediate areas where you could like use it as an amplifier instead of a switch, but let's just talk about it as a switch for now. So when this voltage is above the threshold, this will be shorted and connected. So that would mean that this is really high, right? If we connect this to VDD, it's going to be a large voltage here. This will be connected. PMOS is the opposite. They turn on if their VSG is greater than the threshold. So their source is tied high, while on MOSFETs, your source is tied low. And we can talk about MOSFETs forever. If you understand a MOSFET, like that's the pinnacle thing in electrical engineering that you could understand. But so when this is high, the VSG is low, right? Because if this is VDD and this is VDD, then this is not on. So this will be off, which is that case. And then this will be on because internal signal is VDD. So this is high. And then when this goes low, VGS is going to be off. There's going to be no voltage here. So this turns off. And then because this is like 0 volts, your VSG is VDD, right? It's going to be very large. So this one will turn on.
So PMOS is source to gate, and then
Yeah.
NMOS is gate to source.
Right. Yeah. You can see that I'm swapping like VGS, VSG. You could also think of it as VGS on a PMOS needs to be negative, but usually we just say VSG so that the units are still positive. That way you can think of it as like when it is larger than the threshold, as opposed to like when it is more negative than the negative threshold. Yeah.
So is it just shorting one to? For the push pull, is it just shorting one to ground or one to voltage?
Yeah, pretty much. In reality, it's not a short. It's kind of like this is modeled as a current source. So it'll be like a constant current. But yeah, I mean, that's pretty much the gist of it. You pretty much short it to power or ground. And that's why you're able to like move it so quickly. Yeah, Jared.
Like, what are some trade-offs between like the two? Like, I guess.
Yeah, so like I said, we have a resistor in here that's charging the capacitor. So there'll be some power dissipated by the resistor. So you have to cost more power. Because you have the RC charging, that's going to take longer than a constant current source. So it'll be slightly slower. This one, you have to drive the gate and the source. Like this has to have full range. So it has to be able to drive both of these inputs to the MOSFET from the internal signal. On that one, you only have to drive one MOSFET. So it's the difference between having to drive 2 FETs versus 1. What other trade-offs are there between? In reality, MOSFETs have some leakage. So you are going to have a little bit of current going through here or through there. So that's something to think about. When MOSFETs are on, you can look at the RDS resistor. RDS is like R for resistor between drain and source. So between drain and source, or drain and source. So the RDS on is basically when the switch is fully on, it looks like a resistor. So you can look at that value and see how much power you're going to be dissipating. Yeah, I mean, there's a lot more if you read the specs of the two, but that's some like surface level ones. Yeah, Allison.
Signal or is it like voltage or?
Yeah, I mean, there'll be like a microcontroller. This is basically inside of the integrated circuit. So it could be a microcontroller, it could be a peripheral device. And inside of the integrated circuit, it's like this will have a voltage, and it'll probably be if it's a digital chip, it'll be like a digital to analog converter, a DAC. Like that's what Kaveen was asking if I was going to talk about earlier, which we won't talk about in this one. Maybe we'll talk about it later. But if you want to look it up, there's digital to analog converters, DACs, and analog to digital converters, ADCs. And that's how you switch between the analog and the digital domains. So if it's a digital processor, it'll be driving a DAC to make an analog signal, or maybe there's some analog amplifier in here that's driving this. Yeah.
Analog to like drive this thing.
So like our world is analog, right? Like there's not, you can think of analog as like a whole spectrum of values, and digital is all discretized. So there's only singular steps, like zeros or ones, right? So in reality, you have voltages, which you can have like infinitesimally small voltages, but you can only have like, if you had a digital to analog converter, you can only basically say like, this is 0 volts, or this is 0.1 volts, or this is 0.2 volts, or this is 0.3. Like if my signal was 0.25 volts, my digital domain would just say like that's 2 or 0.2. So yeah, that's the main thing. Like the world is analog, so you always need to go back to analog. Yeah, Alex.
SCM has like a bunch of ADC.
Yeah.
But then it has like 2 DAC pins. Why is it?
Yeah, so you want ADCs, analog to digital, because that's usually how you're sensing analog signals. So if I wanted to sense an analog signal, which is probably what you're doing more often, you would connect that pin to the analog signal, like the accelerator sensor, something like that. Digital to analog converters is if you wanted to drive something, and there's a couple different cases for that I could tell you, but typically you want more ADC pins than DAC pins. Yeah, Nate.
Saying you use an ADC as an input, right?
Yeah, because it'll take in information from the analog world and discretize it into digital for us. All right, now we'll rewind a bit to isoSPI. I'm gonna be honest, isoSPI is probably one of the communications I know the least about. So ask your questions, but this might be a topic to Google more. isoSPI is basically isolated SPI, and it's a communication protocol that was developed by Analog Devices for their battery management chips. The LTC 6811s are the chips that we currently use on our battery pack, but we're switching away from those. But I think the AD-BMS chips still use isoSPI. If anybody here knows if that's confirmed or not, I'm not sure if anybody works on that here. Or anybody that works on that is here right now. They use something called a transformer to isolate the low voltage and high voltage sides of the system. I'm going to say transformers are sort of out of scope for what we're talking about today, but you should look up what they are, just because we're running a bit late on time. So transformers would take a while, but it's basically 2 inductors coupled together. I realize that explanation might have just made it more confusing, but basically it uses current instead of voltage to communicate. So this whole thing is a big loop of wire, and you send a current through the loop of wire, and the transformer will turn that into a voltage that's isolated that can be sensed by the peripheral device on the end. Why this is good for batteries is if a voltage was shorted, the transformer won't allow DC voltage to be transmitted across it. So that's why it's isolated. That's why transformers are considered like isolated components. If one of these wires in the battery got loose and got shorted to high voltage, the DC voltage will not be transferred through the harnessing. Or it would be transferred through the harnessing, but stopped by the transformer. Does anybody have any questions on this? I can try to answer them if they're like more general questions, but yeah.
So, this uses kind of set up what the-
So the other ones we were all looking at like waveforms, right? And they go up for 1 and down for 0. And that's basically a voltage. So either the voltage will be high for 1 or low for 0. This one, we're not actually worried about what voltage is on the wire. Like we're not looking at a waveform going up and down. We're actually looking at a loop of current. And if there's more current, then that's a 1. And if there's less current, then that's a 0. So it's sort of thinking of it as a loop of current. And when that goes high, like that's how we encode our information in the analog world instead of encoding our information as a voltage. Yeah.
2 questions, like why do you need 2 transformers? And then also like why are the wires like coiled?
Yeah, so we're using 2 transformers here because you need the transformers to terminate the line, which we'll explain termination in a second with CAN bus, but you need something on either end of the line to stop reflections, and the transformer is transforming the current signal back into a voltage on the other side to sense it. So, and the reason you need 2 is because we have to make a loop of current, right? You need a full loop for current to flow. If it's broken anywhere, current can't flow if it doesn't have a loop. The reason they're twisted is because it's you twist the pairs to like help stop magnetic interference. So sort of like we were talking last week with circuit fundamentals. If you twist the pairs, they will, well, actually, it's even more applicable here because they're opposite currents, right? So they'll be going opposite ways. So if you get the magnetic field of both of them, those magnetic fields are actually like canceling out as they twist around. So it'll stop like the coupling between the 2 lines. It'll also stop external magnetic fields from like messing with the communication line. Yeah, it's for like signal integrity of coupled and differential signals. All right, CAN bus, the most important one. CAN bus stands for Controller Area Network. Hopefully, a lot more of you know about this because maybe you did it for your recruitment project or something. It has 2 wires, CAN high and CAN low. And this is a differential signal, which basically means that we subtract the 2 from each other, and that's how we get our actual like true signal, the output signal, which means it's tolerant to common mode noise because if something happened to both of them, they're doing the same. So when you subtract that, the common change gets subtracted out. It communicates with dominant and recessive bits. So as you can see over here, a 1 is a recessive bit, and they'll both sit at 2.5 volts, and then CAN bus will pull them apart. So for a 0, it'll send a dominant bit, pull the lines apart to 3.5 and 1.5. Sometimes those values shift a lot depending on what transceiver you're using to drive the bus. And it has termination, which we can see on the left diagram, of 120 ohm resistors on both sides. And so that stops reflections, which basically means if my ECU here on the left drove the yellow line and the green line apart, if I'm driving these lines at a high enough speed, these actually stop looking at wires and we start looking at them as things called transmission lines, which you can do a bunch of reading on. It's good stuff to know for like signal integrity. But transmission lines are basically when your signal is switching so high that the wavelength is, I think it's comparable to like 1/4, or like 1/4 of the wavelength is comparable to the distance of your like transmission line. So basically what that means is the signal looks as a wave propagating down this line. And so basically, let's say it's 0 and I pull it high, that like, it's kind of like when you take a rope and you go like, you whip it, that will propagate down. And as it propagates down, every single next bit of wire that it looks into it'll be like, are you the same impedance as I am currently seeing? So in this case, it's 120 ohms. So let's say I get here, it goes into this and it's like, is it 120 ohms matched impedance? Is it 120 ohms matched impedance? And I ever get to a part like this where there's a junction and I'll see like less impedance, right? Because I can go two ways. I will basically send a second wave back that gets reflected because I hit a like discontinuity in the harness. I'm not doing this full justice, but you can watch a bunch of stuff about transmission lines. It's very important for high-speed communication. Yeah, Lucas.
In the like diagram on the right, why is one of them like pulled apart for longer than the other, but they're both like 0?
I think the diagram that I took from this YouTube video is just poorly drawn.
Okay, so they would be like the same.
They would be, yeah, each bit width would be the same. But yeah, so what I'm getting out of termination is basically you'll send stuff here, there'll be reflections back. And what the termination resistors do is when you see a reflection, it'll actually see the same impedance here. And then this will just like burn the energy when it gets to the end so that it doesn't get reflected back. Also, an added bonus of the termination resistors is they'll pull these two lines close to each other because there's a resistor off here, right? So when you pull these apart, there's going to be some current going through here. And that's why we come back to our common mode, because this will be trying to force the lines back together and the device is trying to force the lines apart. So that's sort of the two forces fighting each other to drive this line. Yeah.
Does it make a big difference for
For the termination nodes or for the devices?
for the devices, like where to see like where dashing or whatever that may be?
Not really, no. I don't think the ordering of devices matters too much. It's just the termination. You need the terminations to be on the ends of the bus. You don't want them in the middle of the bus. Because you want signals to propagate from the middle of the bus out. But when it gets to the end of the line, you don't want it to reflect back into the bus. So you just want your termination to be at the end. Yeah.
Does it just keep it high or keep it like apart for longer, or does it close it down?
Yeah, I mean, it'll basically keep it apart for 2 0 bits. Then one special thing about CAN bus is it can't be the same bit for more than 5 bits. So if I send 5 zeros, what CAN bus will do to make sure it's not broken is it'll do bit stuffing. So it'll actually add a 1 into the message that isn't part of the message after you have 5 zeros. And then the other device will be like, hey, I saw 5 zeros in a row. I should be expecting a 1. And I know that 1 isn't part of the message. It's just there so that I know I'm not broken. Yeah.
How does it like cracking apart like physically happen? The campus, like who sends them?
Yeah, so whatever node is communicating will drive it apart. And the way that works is similar to what we saw with push-pull with 2 switches, is it'll basically have switches to ground for the low and switches to VDD for the high, and it'll just connect those switches or not connect them. And that's how it like drives it or doesn't drive it. Yeah.
Do the resistors prevent them all from being like on the same voltage, because they're all kind of like connected with the resistors, so are like do having the resistors make it so that they're not on the same voltage, I guess, like each wire is on the same voltage.
Oh yeah, the resistors allow you to drive the yellow CAN high and the green CAN low apart from each other. Oh, that's another thing. I like Smith's analogy of if you want to know CAN high from CAN low, they use green and yellow. So CAN high is like the sun. When you look up, it's yellow in the bright sky. And then CAN low is green when you look down at the green grass. I like that mnemonic for remembering which is which. Yeah. Yeah, so your CAN bus will start just like solid, like common mode 2.5 volts. And then when something wants to transmit, it will pull the bus apart. And then what it does after that is it sends its CAN message ID. And so let's say two nodes like the ECU and the keypad pulled apart because they want to start transmitting at the same time. You actually can't really tell in your feedback loop if I pulled it apart or if somebody else pulled it apart at the same time. So then they start sending their CAN message IDs. And so that's why a 1 is recessive, because whichever message ID is lower has more priority. So let's say we're both sending our IDs and we both start with 1. So neither of us are driving the bus. So we think we're good. And then the ECU is probably more important than your keypad, right? So the ECU, let's say the second bit is 0 because it's lower priority, or it's a lower ID, which is higher priority. And then the keypad's second address bit is 1. ECU will drive it apart. Keypad's like, wait, I'm not driving it apart. It should be a 1 right now. And then it's like, oh, something with higher priority must be driving it apart to send the data bit. So keypad will wait for that transmission to end and then try to send its data again. Yeah.
Like, let's say the ECU transmits the signal. Do like all the other ones also get the signal, or is it they have to say like which one should get it? I guess.
Yeah, so everything on the bus can sense these lines, but what you can do on the CAN transceivers and the microcontrollers for each of these nodes is you can set CAN message filters. So that's something you can do on the CS side. You can be like, this node should only subscribe to messages with these IDs. So if it sees something else, it won't waste its time processing that data if it doesn't need that information. Yeah, Allison.
Can Dash communicate, like send signals back to ECU?
Yeah, exactly. They're all connected to the same wires and they're all reading from the same wires. So CAN actually doesn't have controllers or peripherals. Everything has like the same capability to drive and read from the bus. Yeah.
So after we go through the resistors, like how do they actually get power?
The lines?
Yeah.
Yeah, so each PCB will have a CAN transceiver on it, and that CAN transceiver is communicating to the microcontroller over a UART bus. And then that CAN transceiver basically takes in UART, outputs CAN, and then reads CAN and outputs UART to the microcontroller. And internally, it basically has CAN high connected to a switch to power and CAN low connected to a switch to ground. And it'll either like drive it and close those two switches or not drive it and just read it.
But like at the 1-bit level where they're
Yeah.
at like 2.5, like how is that 2.5 volts? How's that voltage like conserved?
Oh, that's actually a good question. I'm not entirely sure of the answer. I think things are just driven to a common mode when they're not powered. Like they have a reference pin that they just power to a common mode. And I know that it stays at 2.5 volts because if they're both at 2.5 volts, there's no current drop across this resistor. So it's not driving them to any other level. But yeah, that's a good question that we should look up in like the CAN transceiver data sheet. Okay, and then a couple more advanced CAN bus things that I added into here because these are some of the things I've been working on to add to the CAN bus to hopefully give us more robustness and stop all the CAN bus errors. There's a lot of things that are going into the CAN bus issue, but this is just a couple of them. So one is split termination. So right, we were talking about just 120 ohm resistor between the two lines. Here, over on the right, you see where it says split termination. And the photo right here actually shows the difference between standard termination and split termination. You actually put half the resistance on the top and the bottom, and then we have a capacitor split in the middle that takes the split node and connects it to ground. So basically, if you had any high frequency oscillations on that node, as your frequency increases, right, the impedance of your capacitor decreases, like we talked about last week at the circuit fundamentals. So the higher the frequency, the more that'll look like a short to ground, and the more it will just dump that power into ground to try to like get rid of it from the line. So this helps with more oscillations, helps with like being more robust to noise. Um, it's the automotive standard that most companies use for how to terminate their CAN bus. So we added that. Then also bus capacitance. I added these capacitors onto the CAN bus lines on each node. They don't have to be populated, but doing things like this in your circuit design is good, like putting pads for components that you may or may not use. Because if I need to add them to like add more capacitance to the line, remember we learned that makes it harder to drive the line, but it also makes it so the line won't move around as much to random variations and oscillations. I added those so that there's pads for you to add components if it's something we wanted to have to try to smooth out the bus. And also ESD protection diodes. These are very good for any signals that you think are going to be touched a lot by people. They help make sure that your microcontroller won't break. If you do insert them, you need to do some thinking and looking at the data sheet because these diodes will add a little bit of capacitance onto the line. So like you can't do it for high speed stuff, but most of the time they're a good call. Yeah, is there any questions about this or other things on? Yeah.
Like, what are the like two little red things like above?
Oh yeah, the two little red symbols next to CAN1P and CAN1N are basically the symbol that assigns a differential net to CAN bus. So when you guys do your circuit boards, make sure to put those. And then when you go into layout, you actually use a different tool to route them. Use the differential routing tool, and it'll make sure that they're the same length. You don't want them to be different lengths because then one might have more delay than the other, and you might be reading one before you read the other one. Yeah.
Also, like, let's say you don't end up putting like the capacitor in, but you still have like the pads there, like you just like fill it in, like how do you fill it in, I guess.
If you put nothing there, like they're not connected. It's just like two pieces of copper that are just like not connected.
Do you need to connect them though? Like,
No, you can just like not populate a component and just like leave the spot empty. Yeah. Yeah, Alex.
Want to talk about the ESC really quick again?
Yeah, so these are basically the ESD symbol that I'm showing on the bottom right over there. The package that I have is two ESD diodes and one integrated circuit package. And it's basically two diodes that the points face each other. And what that's doing is these are Zener diodes. So they will, like diodes, right? We think they only conduct current in one direction. In reality, they're more complicated than that. Even in the forward direction, you'll have a voltage drop over the diode when it conducts. So the first diode allows current to go through, and the second reverse bias diode stops that. And then when the voltage gets higher than the reverse breakdown voltage of that diode, it will start conducting in the reverse direction. So basically, if the voltage on your CAN1P line got too high, it would just shove that all to ground. Now, what voltage do we actually do that at? These ESD diodes are set to 24 volts, so that if your low voltage bus got connected to your CAN bus, it would shove all that power into ground and trip the overcurrent fault of your low voltage bus. So yeah, you want to make sure the ESD protection is going to. It's really meant for like when you touch it, if you have like electric shock and you touch it and you feel like, oh, like that just zapped me. That can actually be in the range of like 16 kilovolts. So this will definitely short that. That's what it's mostly for. But then on the lower end, you also want to size it for like if your low voltage bus got connected to communication. Yeah.
So is it just like when the voltage gets too high, it'll override the other dial that points back and it just conducts?
Yeah. Yeah, if you draw like a diode IV curve, like current versus voltage, it'll look like so this is the voltage and this is the current across the diode. So diodes won't this is not a very good marker. Diodes won't conduct at all, and then they'll hit like their forward voltage, and then they'll sort of go like this. It's not perfectly straight because there is some real component to it, some like linear resistance. And then normal diodes just go like this. And no matter what the negative voltage is, they won't conduct. In reality, eventually, even normal diodes, like they can't block infinite voltage. So eventually they'll break. None of these markers are really good. Eventually they'll break, right? Can you see that? There's that. Okay. So normal diodes will break. Zener diodes are actually designed to also operate in this regime. Normal diodes don't want to operate in this regime. So they'll have some like reverse breakdown voltage, like reverse breakdown. And so it'll come down like this. So in the forward direction, you hit a threshold and it will conduct. In the reverse direction, you hit a threshold and it'll conduct. Yeah.
Like you have ESD to prevent from like high voltages, but like, is there ever a case where you need to fuse like on the CAN bus in case like something pops with high current or like?
Yeah. So that's a good idea. I would say in terms of like high current events, you would put the high current protection on the input of your power like network so that the power network can't pull too much power. Or maybe you also put fusing on the output of your power network so your power network can't source too much power. But the way to think about it for communication is the CAN H pin number 7 on the transceiver, has a very high input impedance. Like you can think of it as a really big resistor to ground because it's just sensing, right? Like we don't want current going into that pin. So it has a high input resistance. So when you have a really high current transient, if it hits that really high impedance, back to like first order principles, voltage is equal to current times resistance, high current, high resistance, I'm going to get a high voltage, and that will get clamped by the ESD protection because it's going to, because the impedance is so high on here, and you also have the capacitors here, like those capacitors will get charged really high, and you'll get a high voltage that will trip the ESD. We got it. I think, else.
Is why wouldn't we just switch the ESD connection out with like a fuse? 'Cause doesn't the fuse just trip every time it gets shorted or it touches high voltage?
Fuses are like current protection, so they'll burn if there's too much current going through them. But physical fuses are actually, they're a little bit wonky because the way you design real fuses that burn is when they conduct a certain amount of current, they heat up a really small conductor, and then that conductor just burns. So it's actually temperature dependent. So if you operated your fuse and you just had like something to cool it down, it wouldn't burn. So we have something, so we have to have physical fuses as per the rules, but on our low voltage boards, the TPS 2482 that we talked about earlier that uses I2C and does all the power telemetry, that's actually an E-fused chip, which is an electronic fuse. So if that thing senses too much current going through, it actually has a MOSFET and it'll disconnect power. And that'll react much faster than a real physical fuse. Also, real physical fuses burn. So when it burns, you have to like go in, desolder it, replace it. You can get PTC resettable fuses, which are a different type of component that will heat up too much, stop conducting current, and then later they'll cool down and continue conducting current. You can use those in some places. There's a lot of places in the rules that they're like, you can't use resettable fuses. Like they only want like fast acting one-time blow fuses. But the thing that these do, like the fuse is going to add resistance into your line because it has to heat up to burn, right? So
Hey, so sorry to interrupt, how long will that take you go?
I think this is the last slide.
You have no time constraint. If I ask questions about that.
Oh, okay. Yeah, does anybody have more questions on this? I think this was, yeah. This is all this is where I got all the photos that you saw in this slide deck, so you can watch these resources as well. And like I said, analog, I would prefer actually like the Texas Instruments application notes better. If you look up like I2C Texas Instruments, they have an entire document that explains to you every single little thing about I2C in like 25 pages. It's really nice. Same thing for SPI, same thing for UART. They're very good. Yeah. Does anybody have any questions before I end the recording that they want captured? So there it is.